And the first paper is light structure from pin motion, simple and accurate point light calibration for physics-based modeling. And the authors are Hiroaki, Santo, Michael Waechter, Masaki, Samejima, Yusuke, Sugano, and Yasuyuki Matsushita. And the talk is given by Hiroaki.
Yes, thank you for your kind introduction. My name is Hiroaki Santo from Osaka University, Japan. First, I explain the research background. Concerning the appearance of a scene, it's determined by these three factors: scene shape, reflectance, and incoming light. Therefore, it's important to know the incoming light. And in this study, we focus on the incoming light and develop a new light source estimation method. We deal with two different types of the light source. One are point light source, which we assume to be an infinitely small point in space, and radiate light source, light equally to all directions. The other is directional light sources, which are infinitely far away from the scene, resulting in parallel lighting. For point light source, we want to know the light source position. For directional light, we want to know the position, want to know the direction. In both cases, the camera may not observe the light source directly, and therefore, the estimation method uses some calibration target to predict the light source position or direction in the camera coordinate. For example, Ackermann's method uses multiple mirror spheres and observes the specular highlight on the sphere. Based on the triangulation strategy, we can estimate the light source position from multiple highlights. Shane's work uses the same strategy, but instead of mirror spheres, it uses one single movable mirror plane, which makes the target a bit easier to prepare. These existing methods use specular highlight on a calibration target. Therefore, they need to detect the accurate position of the specular reflection. However, since the camera observes the reflection of strong light, the highlight becomes very wide, which makes it very difficult to determine the precise position of the highlight center. In addition, sphere-based methods need to know the precise position of the sphere. To achieve this, we need to measure the sphere distance in 3D and fit ellipsoids to the sphere boundary in the image. In our method, we therefore avoid spheres and highlights, and instead use small shadows on a calibration target that is cheap and easy to make. In this figure, on the left side, there is a target camera and light sources. And the board on the right side is our proposed calibration target. Here, I show how our board is made. First, we print 2D marker on a paper and paste the paper on a flat board. After that, we pin needle pins on the board. As you can see, our target board can be made in less than 1 minute. An important point is that you don't need to measure anything. You can just place the needle pins randomly. In a few minutes, I will explain why. As shown in this figure, when we turn on the light source, we can observe the shadow of the pinhead. So if we know the pinhead position, we can easily calculate the light source position from this shadow position. However, it's not necessary for our method to know the pin positions, and we can place the needle pins randomly. Instead, our proposed method observes the track of the shadow while we change the pose of the calibration target, and estimates both the light source position and the pinhead positions. The 2D markers on the target board are used to estimate the pose of board. So let's look a bit into the mathematics. We can regard light source as an inverse pinhole camera. Here we have a traditional pinhole camera. This camera projects object point X to point S on the image plane. Now we replace the pinhole camera with a point light source. So instead of receiving light through a point like a camera, it emits light from a point. So as a result, it projects object point X to point S on the shadow plane. Mathematically, both projections can actually be formulated in the same way. 3D to 2D projection can be formulated by using projection matrices. This is called intrinsics, as you all know, and they contain the focal length and the center, camera's optical center. For shadow projection, the intrinsics contains the coordinate of the light source position. This is called extrinsics. In camera projection, they represent the pose of the cameras. In shadow projection, they are also expressed by the light source position. As a result, this is the projection matrix for point light source. For directional light, we can also formulate this as a projection matrix. As shown, both matrices are very similar, and our method can estimate both cases. In camera projection, considering the problem to estimate projection matrices P and 3D point X from known point S. So this problem is called structure from motion. And in our calibration method, we want to estimate light matrices L and pinhead position X from known shadow position S. Since this is so similar to structure from motion, we call our method light structure from pin motion. Next, I explain how we solve this light structure from pin motion problem. So shadow projection is formulated as in the first equation. To obtain the projection matrix L and pinhead position X, we minimize the reprojection error for all poses and pins. So in this equation, red color represents unknown variables. In structure from motion, this formulation is called bundle adjustment, and it's known to be a non-convex problem. It means that we need a good initialization for this optimization. So I will explain a bit more about initialization. We use the convex relaxation for the initialization. We start from first equation. There are two vectors. One is the vector, green one is the vector from the shadow point to the light source. And blue one is from the shadow point to the pinhead position. These two vectors must be parallel. So our formulation of shadow projection is also from this parallel constraint. This equation can be written as this form. Here I don't explain the details, but these two parts are given parameters, and the red variables are unknown. Lx, Ly, Lz means the light source position, and Cj, xyz means the position of pinhead J. In our method, we relax this equation by treating these second-order variables as independent variables. As a result, we obtain a linear system, whose result we then use as initialization for bundle adjustment. For directional light, the equation looks similar, but for that, please refer to our paper. To solve for unknowns, we need at least 5 poses. Now we come to the evaluation. First, I will discuss a synthetic experiment. Here, I show the result of an experiment where we added noises to the shadow position. First, look at this result. So in a noise-free setup, our method estimates the light position perfectly with only numerical error. And when we introduce larger and larger noise to the shadow position, the estimation error increases as expected. Since we will always have noisy input, we want to have a way to eliminate its influence on the output. One way is, for example, to capture more images of the board in different poses. In this graph, we can see that increasing the number of poses indeed decreases the error. Likewise, you can also decrease the error by putting more and more pins on the board. But for this, please also refer to our paper. Next, I explain our real-world experiment. We performed real-world experiment in 4 environments. E1 and E2 have a point light, and E3 and E4 have a directional light. E1 uses a 3D printed frame for fixing 4 LEDs around the camera. E2 uses a smartphone LED and camera. E3 uses sunlight for directional light. E4 uses a flashlight fixed 3 meters away from the target, and we regard this as approximately directional light. Here we show the estimation error of our method for each environment. So these results depend on the scale of the scene. For example, in environment 1, the distance between target and light source is about 500 millimeters. The light figure illustrates the estimation result for all 4 LEDs in environment 1. Blue point represents the ground truth, and red point illustrates the estimated light position. From the target's perspective and compared to related work, this result is highly accurate. We also show the mean error of the pinhead position for each environment. Accurate estimation of the pinhead position is a good indicator of accurate light source estimation. This is the target board we used in our experiment. Even the largest error that we observed, 2 millimeters, is smaller than the pinhead size of 3 millimeters. So that result also highlights the high accuracy of our method. We also performed a comparison with Shane's method, which uses highlight on a mirror plane. We use environment 1, and for a fair comparison, we hand annotated all shadows and highlight. In this figure, each bar shows the mean error of the light position for our method and Shane's method. This result shows that our method is superior to Shane's method. So conclusion, my take-home message for you is point lights can be estimated like camera with structure from motion. Our method is accurate and simple to facilitate and simple to use. Thank you for listening.
Questions from the audience? Okay, well, I started off with one. Have you thought about degenerate configurations of the pins? Like, I mean, can I use the pins in any position, or is there positions of the pins that I can't use in order to get the calibration?
You mean that there's any limitation for the design of pinhead, a pin position? Mm-hmm. So basically, in our method, there's no limitation for pin position because we show the minimal condition for the estimation. So in that case, in that equation, basically we at least we have only we can estimate from only one pin. So we use multiple pins for robust estimation, but basically at least one pin. So we don't have a limitation for the pin design, but motion have I think there is a limitation.
Okay, thank you. Are there any further questions? Okay, well, with that, let's thank the speaker again